more than 60 years, we have pointed our largest ears at the sky and listened for a voice that is not our own. No one has called back, and that silence is an oddly gentle thing to sit with. Once you know how the listening was actually done, it is easy to hear it as the universe answering no. But set one number beside it. In all those decades, we have listened closely to a few thousand of the nearest stars. Out of the hundreds of billions this galaxy holds, the quiet is real. It is also very small. Tonight we follow that quiet from its beginning. A morning in 1960, when one young astronomer aimed an 85-foot dish at two ordinary stars, the single unrepeated signal that still has no explanation, and the gentle reasons the sky may simply not be speaking our way. Should there be a person in your life who finds the nights long, this is a kind place to send them. For now, let the room go quiet around you, quieter than the sky we are about to search. Nothing here needs an answer from you. You can lose the thread whenever you like, and the voice will keep going. So we begin here, in the listening picture, a hillside in West Virginia, hours before sunrise. Cold enough that breath shows in the dark. A young man sits in a small equipment room with a set of headphones pressed to his ears, listening to a hiss that has been arriving patiently since long before there was anyone to hear it. This is not music he is listening for, and it is not noise for its own sake either. What he wants is a pattern, a rhythm, a repetition, a single structured thing among all the static that would tell him that somewhere out there, another mind had once sat exactly as he is sitting now and had decided to speak. He does not know it yet, but the quiet he is about to record will still be echoing as a question 66 years later. Above him, the great dish turns, slow and patient, following a star that looks, from here, like nothing more than a steady point of light. It is not aimed at anything special. That, in its own way, is the whole point. Tonight, we are going to sit inside that patience for a long while, asking the plainest question a person can ask while looking up at a clear night sky. After all this listening, why has no one called back? The whole shape of that question will unfold slowly, the way it deserves, starting with the single dish on that West Virginia hillside, and widening outward, gently one shell at a time, until the answer arrives the way real answers usually do, without ever needing to become urgent about it. Along the way, we will meet the people who first asked the question seriously. The handful of moments across 6 decades when the sky seemed, for a few minutes, to almost answer, and the long, careful accounting scientists have only recently completed of just how much listening has actually been possible. And, gently, the whole night will end back where it began. At that same quiet hillside, hearing the same static with new ears. There is a version of this story that sounds discouraging, and we are not going to tell that version tonight. We are going to tell the honest one instead, which turns out, again and again, to be a good deal gentler than the discouraging one. Somewhere out past the edge of this room, dishes are turning right now, exactly as they were on that first morning, still listening, needing nothing from us but the willingness to wander along with them while we drift towards sleep. Nearly every real discovery in this particular field has arrived slowly, through long stretches of nothing rather than through any sudden dramatic event, which is not a disappointing fact about this search, but one of its most comforting ones. The whole endeavor has never depended on drama to be worthwhile. It has only ever depended on patience and on the willingness of a small number of curious people across 6 decades now to keep the listening going anyway. Starting on a spring morning in 1960 with the first 2 ordinary stars anyone ever pointed a dish toward on purpose, the young man in that equipment room had a name. Frank Drake, 29 years old, a radio astronomer working at the newly built National Radio Astronomy Observatory in Green Bank, West Virginia, an isolated valley chosen partly because its surrounding mountains kept out the ordinary radio noise of nearby towns. It was the spring of 1960, and Drake had built, essentially by hand, with the help of a small technical team, the first serious scientific search for a signal from another world. The instrument was the observatory's 85-foot Tattle telescope, a wide parabolic dish that could be steered slowly across the sky, fitted with a specially built receiver tuned to a very particular, very narrow frequency. He called the effort Project Ozma, after the princess of a distant, imagined land in a children's book he had loved as a boy. A small private joke about listening for a place that might be every bit as far away and every bit as unlikely to answer as a land found only in a story. Drake did not choose his 2 targets by guesswork. He chose stars that resembled the Sunday closely enough that, if the same kind of chemistry that produced a living, curious planet here had also happened around them, worlds and perhaps something more might have followed a similar path. The first was Seti, a calm, steady, Sunday-like star roughly 11 light-years away, visible in the autumn and winter sky. The second was Epsilon Eridani, slightly closer, a little over 10 light-years out, and notably younger than the Sunday, which made it, if anything, an even more intriguing target, since younger stars in some models leave more time still ahead for anything that might be developing around them. Both stars were visible from Green Bank without any unusual maneuvering of the dish, rising conveniently in the evening sky. Both were, as far as anyone could tell with the instruments of 1960, perfectly unremarkable. That unremarkable quality was the entire argument behind choosing them. If a search like this was ever going to succeed, it made the most sense to start with the stars that looked the most like our own, rather than reaching for anything exotic. He also had to choose a frequency to listen on, and here his reasoning still holds up remarkably well more than 6 decades later. Hydrogen is the single most abundant element in the universe, filling the vast clouds of gas between stars, and every hydrogen atom, everywhere, quietly emits and absorbs radio waves at one specific, unchanging frequency, 1420 megahertz, sometimes called the hydrogen line or the 21 centimeter line. After the wavelength, it corresponds to. Any civilization anywhere that had built radio telescopes of its own would almost certainly have discovered this same frequency early in its own history, because the physics of a hydrogen atom does not change from star to star or from galaxy to galaxy. Drake reasoned that if 2 civilizations wanted to find a common channel without ever having spoken before, the hydrogen line was the most natural meeting place either side could independently arrive at, a kind of universal landmark written into the fabric of physics itself, rather than agreed upon by any culture. It is, in a very real sense, the one frequency the universe already agrees on, long before anyone thought to look for it. For about 6 hours a day, across a few months that spring and summer, Drake and a small team pointed the dish first at Tau Ceti, then at Epsilon Eridani, and simply listened, recording everything the receiver picked up onto reels of magnetic tape for later, careful analysis. All told, something like 200 hours of patient, methodical listening spread across roughly 4 months. And on one of the very first days of the project, something happened that made the whole small room go still. A strong, sharp, regularly pulsing signal came pouring in from the direction of Epsilon Eridani, arriving at a steady, almost mechanical rate that seemed, for a few minutes, entirely unlike the random static the receiver had been recording all along. For a short while, in that small room in West Virginia, it was genuinely possible, as far as anyone present could tell, that the search had succeeded on its very first attempt. Within days of beginning, it did not last. Careful, methodical checking, comparing the signal's exact characteristics against known sources, quickly showed the signal was not coming from among the stars at all. It was almost certainly terrestrial in origin, most likely a passing high-altitude aircraft or a nearby test of a classified radar installation. The two most common sources of false alarms across that entire early era of listening. The signal never returned, despite repeated attempts to find it again over the following days. But that first, brief scare taught the young field its very first and most durable lesson, one that would be relearned gently and repeatedly. Across the following decades of searching, the overwhelming majority of anything unexpected picked up by a sensitive radio telescope turns out, on close and patient inspection, to be us. Our own machines, our own signals, arriving back at our instruments in unexpected forms and from unexpected directions. Before a search like this can ever hope to hear a genuine voice from somewhere else, it must first learn, very thoroughly and very humbly, the sound of its own civilization talking to itself. Project Ozma ran through the middle of 1960 and then quietly, formally concluded that autumn, its verdict, a plain and honest nothing. No repeating pattern beyond that one false alarm, no structured pulse, no voice. And yet nothing about that quiet outcome discouraged the people who had built it, or the wider scientific community that had watched it with such interest. If anything, the project's very existence did the opposite of discourage anyone. A question that had, until that spring, lived only in imagination, in science fiction, and in late-night conversation among a handful of curious scientists, had now been asked for the first time using an actual instrument aimed at actual stars for an actual, carefully logged number of hours. The silence that came back was not a failure. It was the very first real data point in the history of a brand new science, one that up until that point had existed only as a hopeful idea. One man, one dish, two ordinary stars, roughly 200 hours of careful listening, and a question that was everyone quietly understood even then, far larger than any of those numbers alone could capture. In the years that followed, Drake would return often, in talks, and in his own later writing, to how simple the whole setup had actually been. No enormous budget, no international collaboration, just one existing telescope, repurposed with a receiver, built largely from parts already on hand, aimed with patience at two stars any amateur astronomer could have pointed to as well. Part of what makes Project Ozma such a gentle place to begin this whole story is exactly that simplicity. The search for a voice among the stars did not begin with vast institutions or sweeping declarations. It began quietly, almost modestly, with one curious person deciding that a plain, answerable question was worth actually trying to answer, rather than simply wondering about it forever. The observatory itself had only recently been built when Drake carried out his search, tucked deliberately into a quiet valley in the Allegheny Mountains, precisely because the surrounding high ground kept out the ordinary radio chatter of nearby cities. A kind of natural, geological hush wrapped around the whole facility. Even today, the immediate region around Green Bank sits inside a specially protected radio quiet zone, where certain kinds of wireless transmission are restricted by law, so that the instruments there can continue listening for the faintest possible signals without being drowned out by our own ordinary noise. There is something quietly fitting in that arrangement, an entire valley organized, deliberately and by design, around the simple act of making room for careful listening. Word of Project Ozma spread quickly once it became public, drawing far more public attention than Drake himself had expected for what he had originally conceived as a modest, almost private technical experiment. Newspapers picked up the story. A congressional committee took an interest. The idea that a real scientific instrument, rather than a work of fiction, had been pointed at real stars in a real search for company captured something in the public imagination that has never entirely faded since. And yet Drake himself, throughout his long career, remained remarkably measured about the whole subject, treating Project Ozma not as a bold claim about what existed among the stars, but simply as a demonstration that the question could, in fact, be investigated properly, using the ordinary tools of astronomy rather than left forever to speculation and imagination alone. In November of 1961, a small group gathered again at Green Bank, this time not to listen through headphones but to think out loud together. There were about 10 of them in total, an unusually eclectic mix for a scientific meeting of that era. Frank Drake was there, of course, having organized the gathering himself. So was a young astronomer named Carl Sagan, still in his 20s at the time, already known among colleagues for his wide-ranging curiosity. The astronomer Otto Struve attended, a respected figure who had already written publicly about the likelihood of planets around other stars. The physicist Philip Morrison was there too, having co-written, a year earlier, one of the very first serious scientific papers, arguing that a search for radio signals from other civilizations deserved to be taken seriously by the mainstream of astronomy, rather than dismissed as speculation. The engineer Barney Oliver came from the world of industry, bringing a practical, hands-on perspective to the gathering. And the biochemist Melvin Calvin was there as well, though he had to step out partway through the meeting to take an unexpected telephone call informing him that he had just been awarded the Nobel Prize in Chemistry, a detail that has become one of the small cherished anecdotes of that entire gathering. Drake needed some way to organize what promised to be a sprawling, difficult conversation. So before the meeting began, he sketched a simple equation on the blackboard, almost as an afterthought. It was not, and was never intended to be, a prophecy or a firm prediction. It was closer to an agenda for the day, a way of taking one impossibly large, unanswerable question: how many other civilizations might currently exist in our galaxy with the capacity to communicate across interstellar distances, and breaking it down into a handful of smaller, individually more approachable questions. The equation asks you to consider one factor at a time, moving from the broadly known toward the deeply uncertain. First, How many new stars form within the galaxy each year? A figure astronomers, even in 1961, could estimate reasonably well from existing observations. Next, what fraction of those stars turn out to have planets orbiting them at all? Then, among those planetary systems, how many contain a planet that sits in conditions suitable for life as we understand it? Generally meaning a stable orbit at a temperature that allows liquid water to persist on a rocky surface. From there, on how many of those suitable worlds does life actually begin? A question that remains, even today, almost entirely unanswered, because our own planet is still the only confirmed example anyone has ever studied directly. Then, on how many of those living worlds does life go on to develop the kind of sustained, complex intelligence capable of building tools and eventually technology? After that, how many of those technological civilizations choose, at some point in their history, to release detectable signals out into space, whether deliberately or as an incidental byproduct of their own communication? And finally, the last and perhaps most delicate term of all, how long any one civilization continues doing so. Whether that window lasts a few decades, a few centuries, or considerably longer before circumstances change and the signal, for whatever reason, quiets. Multiply all of those individual fractions together, applied against the sheer number of stars in the galaxy, and you arrive at a single estimated figure for how many communicating civilizations might currently share the Milky Way alongside our own. What makes the equation quietly remarkable, more than 60 years after that November afternoon, is how unevenly its individual terms have aged in the decades since. The first two terms, how many stars form and how many of them carry planets, have gone from near total guesswork in 1961 to figures we now know with genuine, hard-won confidence, thanks to decades of patient observation that we will spend an entire later chapter exploring in its own right. The middle terms of the equation, how often life actually appears on a suitable world, and how often that life goes on to develop intelligence, remain almost entirely unknown even now, simply because we still have exactly one confirmed example of a living planet to study in any detail, our own. And the final term, how long a civilization keeps broadcasting before its signal quiets, is arguably the single least knowable term of the entire equation, since our own civilization's answer to that very question is, in a real sense, still being written 1 year at a time by us. This is the honest, almost humble truth about the Drake equation, one that Drake himself was careful to emphasize throughout his career. It was never built to hand anyone a firm number, and it was never intended to settle the question of how much company the galaxy might hold. It was built, deliberately, to show plainly and clearly exactly where our collective ignorance lived, term by term, so that each successive generation of scientists would know precisely which specific question was worth going out and working on next. In that modest sense, the equation succeeded completely and continues to succeed even now. Every space telescope launched in the decades since that meeting, every careful new catalogue of distant worlds compiled since, has been in some quiet and often unspoken way an attempt to fill in one more term of that same blackboard equation first sketched in 1961. The silence we are following together tonight, then, is not a mystery that lacks any structure. It is, instead, a very old, very patient piece of arithmetic, still being worked out one careful term at a time across generations of scientists who will very likely never meet one another, each contributing a small, honest piece toward an answer that may not be complete for a very long time yet. There is something quietly moving in that image, an entire discipline built not around certainty, but around the patient, generational habit of narrowing an honest uncertainty, one careful measurement at a time. It is worth noting too, gently, just how differently that November meeting has been remembered by the very people who attended it. Some later recalled it as a serious, almost formal scientific proceeding. Others, including Sagan himself in later interviews, remembered it more as an informal, freewheeling conversation among friends who happened to share an unusual curiosity, closer in spirit to a long afternoon of thinking out loud together than to a conventional scientific conference. Both memories are probably true at once in their own way. The attendees went on, in the decades that followed, to help shape entire fields, planetary science, the modern search for extraterrestrial intelligence, the careful public communication of astronomy to a wide audience, and yet the meeting that helped set so much of that in motion left behind no formal published proceedings at all. Only Drake's blackboard equation and the shared memory of the small group who sat in that room together for a single November afternoon. That same small, informal group even gave themselves a private name, calling themselves, half-jokingly, the Order of the Dolphin, a nod to the intelligence and evident curiosity of dolphins, which several attendees saw as a useful, humbling reminder that intelligence on Earth itself already takes more than one form, long before any question of intelligence elsewhere in the galaxy was even raised. It is a small, warm detail, easily lost among the larger history, but it captures something true about the whole spirit of that meeting. A group of serious scientists gathered to discuss one of the largest questions imaginable, who still found room for a private joke and a shared sense of wonder along the way. Walk through the equation's 7 terms once more, slowly, the way the room itself must have walked through them that November afternoon. How many stars form each year within the galaxy? What fraction of those stars carry planets at all? Of those planets, how many sit in conditions that could plausibly support life? On how many of those does life actually take hold? Of the worlds that do carry life, on how many does it go on to develop real intelligence? Among those intelligent civilizations, how many then choose, at some point in their history, to release a detectable signal outward? Finally, for however long that signal continues, how many years does it actually last before something changes? 7 terms, each one a separate question a future generation of scientists could, in principle, go and answer on its own, using entirely different instruments and entirely different methods. It is worth noticing how patient a piece of scientific writing this actually is. It does not ask anyone to solve the whole mystery in one sitting. It asks each generation to bring back one honest number and pass the rest along to whoever comes next. Drake himself, decades later, when asked in interviews what number he personally favored for the equation's final result, tended to answer carefully and modestly, noting that the equation had never been designed to produce a single confident number at all, and that its real value lay entirely in the shape of the conversation it made possible, rather than in whatever figure might eventually emerge from multiplying its 7 terms together. That modesty coming from the very person who first wrote the equation on a blackboard, says something worth carrying forward into every chapter still ahead of us tonight. The most useful tools in this whole search have rarely been the ones that promised a firm answer. They have been the ones, like this equation, that simply organized an honest question well enough for the next generation to keep working on it. The summer of 1950 at the Los Alamos Laboratory in the high desert of New Mexico. A physicist named Enrico Fermi was walking to lunch together with 3 colleagues, Emil Konopinski, Edward Teller, and Herbert York, all of them scientists working at one of the most secretive research institutions in the country. The conversation along that short walk had been light and a little playful, drifting, by most later accounts, from a recent magazine cartoon poking fun at a rash of public reports about flying saucers, into an easy, half-serious debate about whether faster-than-light travel might ever, someday, prove physically possible. By the time the 4 of them had settled at the table together, the conversation had already drifted onto something else entirely, an unrelated topic that none of the participants later recalled with much clarity at all. And then, in the middle of that unrelated conversation, seemingly out of nowhere, Fermi asked a question that has since outlived every other detail of that particular lunch. Where is everybody? That was the whole of it. No elaborate setup, no argument attached to it in the moment. His colleagues understood almost immediately what he meant, because the arithmetic sitting behind the question was one that every physicist at that table could work through quickly, in their own head, without needing to write anything down. Given how old the galaxy actually is, and how many billions of stars it contains, and how comparatively quick it would be, on any truly cosmic timescale, for even a slow, patient, sublight speed civilization to gradually spread outward from star to star across the galaxy, filling it the way a slow tide eventually fills every low place along a shoreline. The galaxy ought, by simple calculation, to already be humming with detectable activity by now. And yet, as far as anyone at that table could observe with the instruments available in 1950, the sky appeared, on the surface at least, to be entirely quiet. It is worth sitting for a moment with how small and how thoroughly human this particular moment actually was. This was not delivered as a formal scientific paper. It was not presented at a conference, not written up in any journal, not even planned in advance as a topic for discussion that day. It was one physicist thinking aloud between one passing thought and the next, seated at an ordinary lunch table among friends, in the middle of an otherwise unremarkable working day. What has since come to be widely known as the Fermi paradox is not, in its original and truest form, an argument, and it is certainly not a conclusion. It is a noticing, a single plainly and simply stated observation that the sheer scale of the universe and the apparent quiet of the universe did not, on the surface at least, seem to add up neatly to the same picture. That distinction turns out to matter enormously for how we should think about it, because a noticing invites patient, ongoing investigation, while an argument tends to invite a verdict, a winner and a loser, a closing of the case. Fermi's offhand question has spent the 70+ years since being investigated gently and repeatedly from dozens of genuinely different angles, several of which we are going to walk through carefully later tonight, once we have gathered enough pieces of the wider picture to make each explanation land with its full weight. None of those investigations, close the question completely, even now. What they do instead is soften it considerably, the way careful and patient investigation tends to soften nearly every hard question it is eventually turned toward, showing again and again that a great many ordinary, entirely non-alarming explanations could plausibly account for what looked, from a single lunch table in the summer of 1950, like an entirely empty room. It is worth adding, too, that Fermi himself never treated the question as settled or as cause for concern. By every surviving account from people who knew him, he asked it in the same searching, good-humored spirit in which he approached most of physics, as a genuine curiosity rather than a looming worry. He went on, in the years that followed, to make a rough back-of-the-envelope estimate, suggesting that interstellar travel and settlement, even at very modest speeds, could plausibly fill an entire galaxy within a span of time far shorter than the galaxy's actual age, which only sharpened the puzzle rather than resolving it. But he never treated the puzzle as evidence of anything ominous. He treated it the way he treated most open questions in his long career, as an invitation to keep thinking carefully, rather than a verdict to be feared. The plainest, most enduring question in the entire history of this search, then, was never first asked in a laboratory, and it was never shouted from any podium. It was asked between two ordinary bites of a sandwich by a man who, by every account that survives him, simply wanted in that unguarded moment to know. What makes the story endure decade after decade is partly how ordinary its setting was. Los Alamos in the summer of 1950 was a place devoted to enormous consequential questions, and yet the question that has outlived nearly every other conversation held there, that year arrived almost by accident, tucked inside small talk on an unremarkable walk to the cafeteria. None of the four men present that day thought to write anything down at the time. The exchange survives only because Fermi's colleagues remembered it clearly enough, years later, to recount it when asked, a reminder that some of the most consequential questions in the history of science have arrived not from formal inquiry, but from an idle moment of genuine curiosity, shared casually among friends who happened to be paying attention. In the decades since, researchers have tried, in various ways, to put real numbers behind Fermi's back-of-the-envelope arithmetic, and the estimates that come back are, almost without exception, startling in the same direction his was. Even a civilization expanding at a small fraction of the speed of light, using nothing more exotic than slow, patient, multi-generational voyages between neighboring stars, could plausibly cross and settle an entire galaxy the size of our own within a span of several million years, a period that sounds enormous to a single human life, but is, on the scale of the galaxy's 12 billion-year history, closer to the blink of an eye, repeated many hundreds of times over. That simple comparison, a few million years against 12 billion, is the quiet engine underneath Fermi's plain question, and it is the same comparison that will return in a gentler and more fully developed form later tonight. If the silence Fermi noticed at that lunch table in 1950 was going to mean anything precise at all, the first thing anyone needed to establish was simply how many places there actually were for a voice to plausibly come from. For most of recorded history, that number belonged entirely to the realm of philosophy and speculation, with no way to measure it directly. Today, thanks to one of the great quiet triumphs of modern astronomy, It belongs to the realm of careful measurement, and the measurement itself has turned out to be almost startling in what it ultimately reveals. In 2009, NASA launched a modest, unassuming space telescope named Kepler and pointed it, almost entirely unmoving for years at a stretch, at one single patch of sky, hardly larger than the palm of a hand held at arm's length against the stars. Kepler was not searching for planets by looking at them directly, which would have been essentially impossible given how faint and how close to their parent stars most planets appear from such a distance. Instead, it watched with extraordinary patience and precision for the tiniest, most regular dimming of a star's light, the faint, repeating shadow cast each time a planet happened to cross directly in front of its star, as seen from our vantage point here on Earth. Over 9 full years of steady watching, before the spacecraft was finally retired in 2018, after its fuel and stabilizing equipment were exhausted, it found thousands upon thousands of these tiny telltale shadows, cataloging thousands of confirmed worlds within a portion of the sky so small it represented only a tiny sliver of the whole visible heavens. What Kepler taught the field, more than any single discovery it made, was not simply that other worlds exist somewhere out there. Astronomers had already strongly suspected as much for decades, based on theory alone. What Kepler taught us, with hard observational evidence, was that planets are not some rare or exceptional byproduct of star formation, appearing only occasionally under special circumstances. They are the perfectly ordinary, expected result of it. Wherever stars form from collapsing clouds of gas and dust, it now appears that planets very often form alongside them, almost as a natural, unavoidable consequence of the same physical process. Today, across all the space missions and ground-based surveys that have followed Kepler's lead, including the newer TESS mission launched in 2018, specifically to survey brighter, closer stars across the whole sky, astronomers have confirmed more than 5,000 planets orbiting other stars, with thousands more candidates still awaiting confirmation. The statistics drawn carefully from that enormous catalogue suggest that a very large share of Sunday-like stars, quite possibly the majority of them, carry at least one rocky, temperate world somewhere within their own family of planets. Multiply that fraction against the hundreds of billions of stars estimated to exist within the Milky Way alone, and the resulting arithmetic becomes almost dizzying to hold in the mind all at once. Not thousands of possible homes for something resembling life, not millions either. A number so large, when you work through the multiplication honestly, that the ordinary human mind eventually stops being able to hold it as a picture at all, and can only continue holding it loosely as an abstract idea, the way one holds the idea of infinity without ever picturing it directly. It helps, sometimes, to come at a number that large from a smaller, more human angle, instead of trying to hold the whole thing at once. Consider only the stars close enough to Earth that a signal traveling at the speed of light could reach us within a single ordinary human lifetime, say, within about 80 years of travel time. That modest sphere alone, a comparatively tiny bubble within the wider galaxy, still contains many thousands of stars, and following the same statistics drawn from Kepler and its successors, very plausibly tens of thousands of planets among them. A search restricted only to that near, human-scaled neighborhood, the closest possible slice of the sky, is already a larger undertaking than anything Drake could have imagined listening to in 1960, and it represents only the barest, nearest sliver of the full count waiting further out. It is worth pausing too on how recently all of this became knowable at all. For nearly the entire history of astronomy, going back thousands of years to the earliest recorded observations of the night sky, no one had any direct, confirmed evidence that a single planet existed anywhere beyond our own solar system. The first confirmed detections of planets around an ordinary, Sunday-like star did not arrive until the middle of the 1990s. In the span of one working astronomer's career, the field moved from total uncertainty, a complete unknown occupying the most important term of Drake's original equation, to a confirmed catalogue of thousands of worlds and growing. Very little in the entire history of this search has changed as quickly or as generously as our answer to the simple question of how many doors there actually are. This is the single piece of the whole puzzle that has changed the most dramatically since Drake first stood at that blackboard in November of 1961. The most uncertain term in his entire equation at the time, how many planets actually exist for life to potentially call home, has since been answered, and answered with remarkable generosity by the universe itself. There are doors everywhere we now look carefully enough to count them, which means that the silence Fermi noticed, if we are going to keep taking it seriously as an honest puzzle rather than dismiss it, cannot be explained away simply by suggesting there was nowhere else for anything like life to have taken hold. The homes themselves are there, in numbers too large for anyone to reasonably argue with. Whatever precisely is keeping the wider sky quiet, it is clearly not, at its root, a simple shortage of worlds. It is something else, sitting somewhere further along in the equation, in one of the terms we still cannot measure directly. And it is to that deeper uncertainty that we now gently turn our attention. There is value in lingering for just a moment longer on how Kepler actually accomplished all of this, because the method itself is a quiet, patient marvel in its own right, and it says something true about the character of this whole search. The telescope never once photographed a planet directly. Nearly every world in its enormous catalogue was found only indirectly, by watching a single star's light dim by a fraction so small, often less than 1 part in 10,000, that no human eye could ever hope to notice it, and waiting patiently for that same tiny dimming to repeat again and again at a regular interval before the signal could be trusted as a genuine planet rather than a passing coincidence. It is the same discipline we will meet again and again tonight, the same insistence on checking and rechecking and waiting for confirmation before allowing any real excitement. Applied here not to a radio signal, but to the barest flicker of starlight. Since Kepler's own retirement, its work has been extended by newer missions built with the same patient philosophy in mind. The TESS mission, launched in 2018, surveys the entire sky in wide overlapping sections, rather than staring fixedly at one small patch, specifically to find planets around brighter, nearer stars, the ones best suited for the kind of detailed, patient follow-up study that comes next. Ground-based observatories, meanwhile, have refined a separate technique entirely. Watching for the tiny rhythmic wobble a star exhibits as an orbiting planet's gravity tugs it gently back and forth, a method that first confirmed a planet around a Sunday-like star in the middle of the 1990s, and has continued adding to the catalogue ever since. Between these methods and others still being refined, The count of confirmed worlds continues climbing steadily, year after year, with no sign yet of slowing down. 66 years of patient, careful listening have not been entirely without a small handful of moments that made everyone involved sit up straight and hold their breath for a while. There have been 4 such moments in particular, spread unevenly across the decades. Each one examined with real scientific care, and each one, in the end, honestly explained. The first came in late 1967, though it was not born from any deliberate search for other civilizations at all, which somehow makes it a gentler story rather than a lesser one. A young graduate student at Cambridge University named Jocelyn Bell Burnell was patiently combing through miles and miles of chart paper recorded by a radio telescope she had personally helped design and build, when she noticed something unusual tucked among the ordinary static. A precisely repeating pulse, arriving once every 1 1/3 seconds, with a metronomic regularity that no known natural process was thought, at the time, to produce. For a short while, in a private, half-joking exchange within her own small research group, the signal was informally labeled with the initials LGM, standing for Little Green Men, purely as an inside joke about how mechanically regular it seemed. It turned out to be something almost as astonishing in its own right, though entirely natural, and once understood, deeply beautiful in its own way. It was the very first ever detection of a pulsar, the rapidly spinning, incredibly dense collapsed core left behind after a massive star reaches the end of its normal life, sweeping a narrow beam of radio waves around and around like a vast, silent, cosmic lighthouse. The discovery would eventually earn a Nobel Prize for 2 of Bell Burnell's senior colleagues, born from a signal that had, for a few private, playful days, briefly looked to its own discoverer like it might be a genuine message from somewhere else. A decade later came the second almost, perhaps the single most famous, 72 seconds in the entire 6-decade history of this search. On the 15th of August, 1977, the Big Ear Radio Telescope, operated by Ohio State University, recorded an extraordinarily strong, narrow signal arriving from the direction of the constellation Sagittarius and landing remarkably close to that same hydrogen line frequency Drake had chosen back in 1960 as the most natural meeting place in the whole radio spectrum. Days later, when the astronomer Jerry Eman sat down to review the long printout by hand, as was the routine at the time, he circled the sequence of characters representing the signal's measured strength, 6EQUJ5, a code the telescope used to record intensity, and almost without thinking, wrote a single word beside it in red pen. Wow. The signal has never once been detected again, despite a great many careful, patient attempts over the following decades to look again at that exact same patch of sky using that same narrow frequency band with increasingly sensitive instruments. To this day, it remains formally unexplained, neither confirmed as anything extraordinary nor ever fully accounted for by any ordinary, mundane cause anyone has been able to identify with confidence. It sits quietly and patiently in the observational record as the single most tantalizing 72 seconds this entire search has ever produced. A genuine, honest mystery rather than a solved case filed away and forgotten. The third almost unfolded far more slowly, over the better part of a decade, and turned out, in the end, to be the gentlest and most thoroughly human explanation among the four. For a long stretch of years, the Parkes Radio Observatory in New South Wales, Australia kept detecting unexplained bursts of radio noise, arriving only during the observatory's own daytime working hours, which puzzled and mildly frustrated the astronomers there for the better part of 10 years. In 2015, careful, methodical investigation finally traced the true source of the mystery. It was the observatory's own staff kitchen microwave oven, its door being opened a few seconds before its cooking cycle had fully finished, letting out a brief, sharp burst of stray radio energy each time someone, hungry and impatient, checked on their lunch a little too early. An entire minor, decade-long mystery of professional radio astronomy, solved not among the distant stars at all, but down the hallway next to the kettle and the shared refrigerator. And the fourth and most recent almost arrived in 2020, when researchers combing carefully through archived telescope data as part of the ongoing Breakthrough Listen program, noticed a narrow, unusual signal that appeared to be arriving from the general direction of Proxima Centauri, our very nearest stellar neighbor, at just over 4 light-years away. It was examined with enormous, deliberate care over many months, given the working designation BLC-1 for Breakthrough Listen Candidate 1, and after extensive, painstaking cross-checking against known sources of interference, was ultimately traced, with reasonable confidence, to ordinary, mundane human-made radio interference originating here on Earth itself. 4 almosts spread unevenly across more than half a century of careful listening. Not one of them ultimately survived close, patient examination as a genuine signal originating from somewhere else. And yet notice, gently, what each of these 4 moments actually has in common. None of them were ever simply ignored or quietly set aside. None were explained away casually, without real investigation. Each one was checked and rechecked, and in most cases, checked again by entirely separate research teams, using entirely separate instruments and independent methods, precisely because the whole discipline of this field succeeds or fails on its own willingness to talk itself patiently out of good news whenever the evidence calls for it. That discipline is not, in any sense, a weakness of the search. It is, quite plainly, the very reason a real detection, whenever it finally comes, if it ever does come, would actually mean something lasting and trustworthy, rather than simply being one more excited false alarm added to a long and honest list. There is a 5th moment, smaller than the other 4 and less widely remembered, that belongs here too, if only briefly, because it shows how the same careful discipline applies even to the smallest signals. In the 1990s, a candidate signal picked up during Project Phoenix, the privately funded successor to NASA's own defunded search, appeared briefly promising enough that the observing team followed the standard procedure built specifically for such moments, quietly requesting time on a second, distant telescope to check whether the same signal could be confirmed independently. It could not. The signal turned out, once again, to be terrestrial interference, and the entire episode passed almost without public notice, exactly as the underlying procedure is designed to ensure. That quiet, almost anticlimactic outcome is, in its own understated way, one of the most reassuring details in this whole history. The protocol built to verify a genuine detection has been tested many times over the decades, on candidate after candidate, and has, so far, worked exactly as intended every single time, gently ruling out everything that has not held up to scrutiny. It is worth adding, gently, one further reassurance about how any of this would actually unfold if a real signal were ever confirmed. There is a long-standing, informally adopted set of protocols within the field, first drafted in the 1980s and refined since, describing how researchers should verify a candidate signal, whom they should notify, and how any such discovery should be shared openly with the wider public and the scientific community, rather than kept quiet or announced hastily. Nothing about this whole search has ever been designed to produce a sudden dramatic reveal. It has been designed patiently and deliberately from its very first days at Green Bank to produce a confirmed, careful, trustworthy answer whenever that answer finally arrives. Here is where the whole shape of tonight's question begins to turn, gently but decisively. Because for all the careful listening that has been done since that spring morning in 1960, there is a plain, sober accounting that almost no one outside the field itself ever actually hears about. In 2018, a small team of researchers led by the astronomer Jason Wright sat down and tried, for perhaps the first time in this field's history, to honestly and rigorously measure something that had never been carefully measured before. Not whether other civilizations exist somewhere among the stars, which remains entirely unknown, but something more modest and in its own way more useful. Out of everything that could theoretically possibly be searched, how much of it have we, as a species, actually managed to search so far? A search of this kind does not have just one single dimension, the way a simple survey might. It is not merely a matter of pointing enough dishes at enough stars and waiting. A truly complete search would need to sweep across an enormous range of possible radio frequencies, because we simply do not know in advance which particular frequency, if any at all, another civilization elsewhere might have chosen to use. It would need to consider an enormous range of possible signal strengths, because we do not know how powerful or how faint a distant transmitter might reasonably be. It would need to account carefully for timing, because a genuine signal might arrive for only a few seconds or a few minutes, once in a very great while, and then never repeat again within the lifetime of anyone listening. And it would need to account, too, for the sheer staggering number of individual stars worth checking in the first place, which, as we now know clearly from Kepler and everything that has followed it, numbers in the hundreds of billions within our own galaxy alone. When Wright's team carefully multiplied all of those separate dimensions together, arriving at a kind of total theoretical search volume, and then compared that full volume against everything that has actually physically been searched across the entire recorded history of this field. From Project Ozma in 1960 right up through the most modern surveys, the resulting fraction that came back was almost impossibly small, smaller than most working scientists in the field themselves had casually assumed going in. Let that finding settle for a moment, the way it genuinely deserves to. We have not searched a large portion of the available sky and come back empty-handed. We have searched a portion so small, so vanishingly thin, that describing it honestly requires reaching for a very careful, very deliberately chosen way of thinking about scale. Because the ordinary comparisons people usually reach for badly understate it. Picture, then, instead of the wide ocean, someone might instinctively reach for something quieter and more intimate in scale, a single, truly enormous library, its shelves stretching further than the eye could ever hope to follow in any direction, holding within it every single book that has ever been written, in every language, across the entire span of human history. And picture that, in the entire time this search has existed as a formal scientific effort, we have managed collectively to open and carefully read exactly one page from exactly one book, taken essentially at random from exactly one shelf, somewhere in that impossibly vast collection. That single page told us nothing at all about any voice calling out to us from elsewhere. But it would be a hasty thing, wouldn't it? To close that one page, quietly set the book back onto its endless, unexplored shelf, and then declare with any real confidence that the entire library beyond it must therefore be silent and empty. This, gently, is the honest answer to the through line we have been carrying together since the very first minutes of the cold open tonight. What does the silence actually tell us after 66 years? It does not tell us with any real confidence that no one else is out there among all those countless stars. It tells us plainly and without any need for drama or alarm that we have barely finished asking the question in the first place. The most serious modern instrument in this whole search, a 10-year, privately funded program called Breakthrough Listen, publicly announced in 2015, with considerable fanfare, set out with the explicit, stated goal of carefully examining roughly 1 million of the very nearest stars, using some of the largest and most sensitive radio dishes ever built for this purpose, including the very same Green Bank site where Drake first listened. Its published surveys so far, careful, rigorous, painstaking work, carried out by dedicated teams over many years, have covered a number of individual stars, sitting only in the low thousands. A single page from a single book on a single shelf in a library simply too vast for any one lifetime, or even several lifetimes strung together, to finish reading. It is worth walking through, gently, why the search has necessarily moved this slowly, rather than treating the slowness itself as some kind of failing. Every additional hour of telescope time devoted to this search is an hour taken away from other, equally worthy astronomical work, careful studies of star formation, of distant galaxies, of the weather on nearby planets, all competing for the same limited number of large dishes and the same limited number of clear observing nights. For most of this field's history, funding for a dedicated search of this kind was scarce, often provided by private donors rather than national space agencies, which meant the pace of listening was always constrained by resources rather than by any lack of scientific interest. Breakthrough Listen itself exists only because of a substantial private donation made in 2015 specifically to give this particular question the sustained attention it had rarely received before. Even with that generous support, the mathematics of the haystack remain what they are. A single well-funded decade of careful listening, however diligent, can only ever open a small handful of additional pages in a library built from hundreds of billions of books. There is a gentler way to hold this same fact, one that turns the scale of the haystack from something faintly overwhelming into something closer to a quiet invitation. Every single year, the tools available to this search grow more capable. Receivers grow more sensitive. Computers grow fast enough to sift through vastly larger volumes of recorded data than they could when Drake was working with reels of magnetic tape. Whole new techniques, like the optical searches we will meet later tonight, open entirely new pages of the library that were simply inaccessible before. The fraction of the haystack searched so far may be small, but it has never once shrunk, and it grows a little larger with each passing year, carried forward by the same patient curiosity that first sent one dish turning toward two ordinary stars back in 1960. If the sheer size of the haystack itself explains a great deal of the silence we have been sitting with tonight, there is a second, quieter possibility layered underneath it, one that has almost nothing to do with how much of the sky we have searched, and everything to do with time itself, and the particular scale time takes on once you start thinking about an entire galaxy rather than a single lifetime. This is the vastest and quietest idea we will sit with together tonight. So let it arrive slowly, the way it deserves to. Even at the very nearest possible star to our own, a question sent outward and its answer received back are separated, at an absolute minimum, by more than 8 years of travel time, simply because that is how long light itself, moving as fast as anything in the universe is permitted to move, takes to make the full round trip there and back. Reach a little further out, to the far side of our own galaxy, and that same simple exchange stretches to roughly 100,000 years each way, a span of time longer than the entire history of anatomically modern humans on Earth. A genuine conversation carried out across the width of the galaxy, if it were ever even attempted by anyone, is therefore not measured sensibly in minutes, or in years, or even in ordinary human lifetimes. It is measured more honestly in something closer to the span of entire civilizations quietly rising, settling into their own particular rhythms, and eventually changing beyond recognition, all before a single reply could ever arrive. Now add one further piece to the picture, gently, because it changes everything that follows from here. The Milky Way galaxy itself is more than 12 billion years old, considerably older than the Sun and the Earth, which are each roughly 4.5 billion years old by comparison. Stars have been quietly forming and worlds forming patiently around them for nearly the entire immense stretch of that 12 billion year history. And yet, for all we currently know or can reasonably estimate, any single civilization capable of sending out a detectable signal into space might only continue doing so for a relatively short window, perhaps a few centuries at most, before its own methods change. Its technology quietly moves on to something quieter and more efficient, or its collective attention simply turns toward other things entirely, a pattern we ourselves, as it happens, have already begun to follow, a point we will return to shortly in its own right. Set those two facts gently beside one another. Now, the way this whole evening has been gradually asking you to do with each new piece we gather. A galaxy old enough to have potentially hosted an almost uncountable number of separate civilizations scattered across its long, patient history, and yet each one of them, if it existed at all, might have only been detectable for a few brief centuries out of an available 12 billion years. Two such neighbors could very easily and very innocently miss each other entirely, not because either one of them was ever too far away in simple distance, but because neither one happened to be listening or broadcasting, during the same narrow window of time. Picture, if it helps, two houses standing on an impossibly long street. A street so long, it would take 100,000 years simply to walk from one end of it to the other, where each house lights its own porch light for only a single evening out of an entire century of standing there. Even if every single house along that impossibly long street eventually does light up at some point across its long history, the odds that any two particular houses happen to be lit on the very same night out of 100,000 years of nights are vanishingly, almost immeasurably small. This is not, in the end, a bleak thought to carry with you tonight, even though it might sound like one at first hearing. It is, in its own quiet way, a deeply gentle one. Instead, it suggests that the silence we have been sitting with together may not be any kind of census at all, any kind of final headcount of who is out there and who is not. It may simply be a scheduling problem, playing out patiently across a span of time far too large for any single mind, however careful, to hold comfortably all at once. The sky may not be empty of neighbors in any permanent sense. It may only be, on any given night, and for entirely ordinary reasons, empty of neighbors who happen to be listening or speaking at exactly the same passing hour that we are. Stars themselves live out this same lesson in miniature, in a way that makes the whole idea easier to hold. Our own Sunday is a middle-aged star, roughly 4.5 billion years into an expected lifetime of about 10 billion years, meaning it sits close to its own halfway point. But the galaxy holds stars at every conceivable stage of that same long arc. Some newly formed within the last few million years, their planetary systems still settling into stable orbits, others far older than the Sunday. Their own planets, if they ever had any, having circled quietly for twice as long as ours have. A civilization arising around one of those older stars might have already lived through its entire broadcasting era and moved on, long before our own Sunday had even finished forming. A civilization arising around one of the younger stars might not exist yet at all. Its planet still cooling, its chemistry still settling, its own first Frank Drake not due to be born for another billion years. Any two civilizations we might imagine meeting are drawn, essentially at random, from an enormous, staggered span of possible starting times, not from a single shared moment, the way two people might casually meet at the same party. Astronomers sometimes describe this using the gentle image of a chorus that never fully assembles, where singers arrive one at a time across a span of centuries, far longer than any single voice can sustain a single note, so that the whole choir is never present in the room together, even though every voice that ever sang was, in its own time, a genuine part of the same performance. It is a useful image to hold on to here, because it reframes the silence, one more time, away from absence and towards simple timing, the same quiet reframing this whole chapter has been offering. One gentle image at a time, there is a further, more hopeful way to hold this same long arithmetic, one that looks forward rather than back. If a civilization's broadcasting window really does last only a few centuries before it changes or grows quieter, as our own appears to be doing already, then two neighboring civilizations separated by, say, 100 light years, close enough that a signal could cross the gap comfortably within either side's own broadcasting lifetime, stand a meaningfully better chance of overlapping than two neighbors separated by tens of thousands of light years. The long wait between signals is not, in other words, a single fixed obstacle applying equally everywhere. It shrinks gently the closer two civilizations happen to sit to one another, which is part of why so much of the careful listening described tonight has focused first on the nearest stars, the ones where the timing problem is smallest and the odds, however modest, are least unfavorable. There is one more piece to this deep, quiet middle of tonight's story, and it may turn out to be the gentlest piece of all, because it turns the telescope back around, quietly, to face us instead. For decades now, our own televisions, our radio stations, and our radar installations have all been leaking faint radio energy outward into space, quite unintentionally, spreading outward in every direction at the speed of light, the same way any radio transmission naturally does. It is tempting, at first, to imagine this steady leakage as a loud, unmistakable announcement of our presence, a wide wall of noise that any sufficiently advanced listener elsewhere would easily and immediately notice. Careful analysis, going back to studies conducted from the 1970s onward and refined considerably since, tells a much quieter and more modest story than that instinct suggests. Our ordinary broadcasts, the everyday hum of television and radio programming, spread outward and grow fainter with distance so quickly, following simple and well-understood physical laws that an instrument exactly like our own most sensitive radio telescopes, if it happened to be sitting even just a few light years away and listening specifically for exactly this kind of ordinary signal, would very likely not be able to pick it out clearly from the general background noise of the galaxy at all. The loudest things Earth has ever deliberately or incidentally sent outward into space are not, in fact, our entertainment broadcasts or our everyday conversations. They are instead a comparatively small handful of narrow, powerful, deliberately focused transmissions, most notably the beams used by planetary radar systems, such as those historically operated from Asabo and Goldstone, studying nearby asteroids and other planets within our own solar system, alongside the tight, purposeful signals used by certain military and civilian radar installations here on Earth. These are brief, highly focused, occasional events by their very nature, rather than any kind of steady, continuous broadcast that a distant listener could simply tune into at any convenient hour, the way one might tune into a familiar radio station. And here, gently, is the quietest turn of this entire chapter. We are, if anything, steadily becoming harder to notice from a distance with each passing year, rather than easier as our own technology continues to advance. The tall broadcast towers that once filled the air around us with radio energy, spreading it generously in every direction, are being steadily replaced by underground cables, fiber optic lines, and satellites that beam tightly focused signals directly between two specific points, rather than scattering that same energy outward wastefully into the surrounding sky. Our own accidental leakage into the wider cosmos, measured honestly and carefully over time, is not, in fact, growing louder as our civilization continues to advance technologically. It is quietly, steadily fading generation by generation, exactly the way a bright light dims once someone finally learns to aim it more efficiently, which leaves us gently with an answer to tonight's through line that is almost startling in just how fair and how evenly it applies to everyone involved. If another civilization somewhere, at a fairly typical distance, using instruments no better than our very own best current technology, were listening carefully for a planet exactly like ours, they would, in all likelihood, hear nothing at all worth noting. By our own honest standard, the very same standard we ourselves use to quietly judge everyone else's apparent silence, Earth has never truly called anyone back either, not in any way a distant listener could easily detect. We are not simply the patient audience, waiting endlessly for some outside voice that stubbornly refuses to answer us. We are, in our own quiet and largely unnoticed way, one more house standing along that same impossibly long street, our own porch light flickering briefly on for only the briefest moment before dimming quietly again into the dark. There is a further, quieter wrinkle worth sitting with here, because it deepens the same fairness rather than undercutting it. Even our loudest deliberate transmissions, the planetary radar beams used to study nearby asteroids, are aimed with great care at specific, chosen targets within our own solar system, not scattered broadly outward into the wider galaxy. A civilization elsewhere would need to happen to be sitting almost precisely along the narrow path of one of those beams, at almost precisely the right moment to intercept it at all. Extend the same reasoning outward, and it becomes easy to imagine an entire galaxy quietly full of technological civilizations, each one occasionally sending narrow, purposeful signals toward their own nearby worlds and moons, each one almost entirely invisible to every other civilization, simply because none of those narrow beams happen to be aimed at each other. A galaxy can be, in this sense, quietly busy and quietly silent at exactly the same time, depending entirely on which direction you happen to be listening from. Researchers have tried, in recent years, to put an honest number on exactly how far our own accidental radio leakage could plausibly travel and still be noticed by an instrument as sensitive as our own best current receivers. The figures that come back are humbling in a gentle way. Our strongest, most persistent leakage, mostly older analog television and radar signals from the middle of the 20th century, would likely become undetectable to a telescope, like our own somewhere within a few dozen light years, a distance that sounds considerable until it is set beside the 100,000 light-year width of the galaxy as a whole. Within that modest bubble sit only a small handful of stars. Beyond it, for the overwhelming majority of the galaxy's hundreds of billions of stars, Earth has, for its entire broadcasting history so far, been functionally silent, regardless of how much television and radio we ourselves have enjoyed listening to at home. With the true shape of the haystack now held gently in view, and the long, patient wait between any two signals held gently in mind alongside it, we can finally walk carefully through the honest range of explanations this field has offered, over its 6 decades of careful thought for the silence we have been sitting with together tonight. We will take them calmly, one at a time, none of them presented here as any kind of final verdict. Each one simply a gentle possibility worth sitting with in turn. The first, and in many ways the simplest, is this: we may quite plainly be early. The universe itself is roughly 13,800 million years old by the most careful current measurements, and star formation is expected by every model astronomers currently trust to continue steadily for a very long stretch of time yet to come. far longer than the universe's current age already spans. Small, dim, reddish stars in particular, which are considerably more common throughout the galaxy than stars like our own comparatively short-lived Sunday, are known from careful stellar physics to burn steadily and quietly for trillions of years apiece, vastly longer than the Sunday's own expected total lifetime of roughly 10 billion years. If most of the universe's eventual homes for life have genuinely not yet finished forming, or have only just begun their own long, stable stretch of quiet stability, then it may simply be that most of the story the universe intends eventually to tell has not yet properly started. We may, in this gentle reading, be reading only the very first page of a very long book, arriving hopefully early, before almost anyone else has had the chance to arrive at all. The second gentle explanation is often called, informally, the rare earth idea. It suggests that while planets themselves are demonstrably common, exactly as Kepler taught us so clearly and so generously, the exact specific chain of circumstances that kept this particular planet stable and hospitable across billions of years, a proportionally large moon that steadies our tilt and our seasons, a particular kind of protective magnetic field that shields the surface from harmful radiation, active plate tectonics that patiently recycle the crust and regulate the atmosphere over billions of years, may together represent a considerably rarer combination of circumstances than simply having any planet at roughly the right distance from its star. Under this gentle idea, the basic ingredients for life might turn out to be common almost everywhere. Astronomers look carefully, while the specific fragile recipe that allows life to flourish undisturbed for billions of uninterrupted years might prove to be considerably harder to come by than the ingredients alone would suggest. And the third gentle explanation asks us to carefully separate two things we often blur carelessly together in casual conversation: simple life itself and intelligent, technological life capable of reaching outward. Life appeared here on Earth remarkably early in the planet's own history, quite likely within its first several 100 million years of existence, almost as soon as conditions allowed it at all. And yet more than 3 billion years passed after that. The overwhelming majority of this entire planet's long history, before anything living on it ever built so much as a single radio telescope. If that same long, patient gap holds true elsewhere across the galaxy, then simple life itself might turn out to be reasonably common, appearing readily wherever conditions allow, while the particular later kind of intelligence capable of reaching out across interstellar distances might remain, for the time being at least, a much rarer and considerably later arrival on the cosmic stage. None of these three gentle ideas argue directly with one another, and none of them, taken alone or together, fully closes the question we have been carrying tonight. They simply widen, honestly and carefully, the range of quiet, entirely ordinary reasons the sky might not yet have answered us, each one perfectly consistent with a universe that is not empty in any final sense, only patient, unfinished, and still quietly unfolding. There is a fourth, closely related idea worth including here, sometimes called the Great Filter, though we will hold it as gently as the other three, rather than treating it as any more certain. It suggests that somewhere along the long chain running from simple chemistry to simple life, to complex life, to intelligence, to technology, to a civilization that endures long enough to reach across interstellar distances, there may sit one especially difficult, especially rare step, a kind of narrow gate that very few planets ever manage to pass through. If that difficult step lies somewhere behind us, in our own deep past, then our own presence here tonight, listening and wondering, is itself a small, quiet triumph, evidence that we happen to make it through a gate that closes behind most of the planets that ever try. If the difficult step instead lies somewhere ahead of us, still unmet, that would be a heavier possibility to sit with quietly, though even here, honest uncertainty is the only fair conclusion available, since we have no way yet to know which direction, if either, the filter actually sits. What all four of these gentle explanations share, and what makes them worth holding together, rather than picking a single favorite among them, is that not one of them requires anything unusual or exotic to be true. They require only ordinary astrophysics, ordinary biology, and ordinary statistics, applied patiently across spans of time and space, too large for any single mind to intuit correctly on its own. The universe under every one of these readings remains exactly as vast and exactly as promising as Kepler's careful catalogue of worlds suggests. What varies from one gentle explanation to the next is simply how that vast promise happens to be distributed across time. A variable this search has always found far harder to measure than simple distance. It is worth remembering, too, that these four gentle explanations are not the field's final word, only its current, honest best guess, offered the same way every other figure in this whole search has been offered, as a careful estimate, awaiting better evidence. Each new space telescope, each new catalogue of nearby worlds, each new careful study of Earth's own earliest biology narrows the range of guesswork by a little more. The scientists working on this question today do not expect to resolve it personally, any more than Drake expected to resolve his own equation the afternoon he first sketched it on that blackboard. They expect, instead, to hand a slightly clearer picture to whoever comes next. The same quiet generational relay this entire search has always run on. There is a second set of explanations, quieter still than the first, that turn the question away from whether anyone else is out there among the stars at all, and gently toward a somewhat different possibility that we ourselves might simply be listening in the wrong particular way, for the wrong particular thing. Consider, first, the honest question of frequency. Drake's original choice of the hydrogen line back in 1960 was thoughtful and well-reasoned. But it was still, in the end, a choice, one sensible assumption among several other possible ones. Later researchers proposed a slightly wider band, sometimes called informally the water hole, sitting quietly between the hydrogen line and a second natural frequency associated with the hydroxyl molecule, reasoning carefully that this calm, relatively interference-free stretch of the radio spectrum might make for an especially sensible shared meeting place between two civilizations who had never previously spoken. It is an elegant, thoughtful idea, and it has guided a great deal of the searching described tonight. It is also, quite honestly, still fundamentally a guess about what another, entirely unknown civilization might independently consider obvious, built necessarily from what merely looks obvious to us, given our own particular history and our own particular instruments. Consider, too, the honest question of medium entirely, setting frequency aside for a moment. Nearly all of the careful listening described throughout tonight's whole story has relied on radio waves specifically, simply because radio was the available, practical technology at hand when this search first began back in 1960. In more recent years, researchers have started building entirely new instruments to watch for something rather different, extremely brief, precisely timed pulses of visible light or infrared light, a newer technique sometimes called optical search, reasoning that a sufficiently advanced civilization somewhere further along its own technological path than we currently are might well prefer a tightly focused laser over an old-fashioned radio transmitter, in much the same way our own engineers here on Earth now increasingly favor fiber optic cables over old broadcast towers for exactly the same practical reasons of efficiency and focus. If another civilization made that same technological choice decades or even centuries ago, all of our own patient listening in radio frequencies alone would have been aimed, however carefully and however diligently, in entirely the wrong direction the whole time. And consider finally the honest question of duration, returning briefly to an idea we touched on earlier tonight. If Earth's own broadcasting era turns out, in hindsight, to have been a comparatively brief flash in time, several decades of louder, leakier radio activity followed by a long, quiet transition toward tighter, more efficient, and more deliberately focused technology, then it stands to reason that every civilization's own broadcasting era might follow a similarly brief pattern, a short, noisy technological adolescence, followed by a much longer, quieter technological adulthood. Two entirely separate civilizations might both genuinely exist at the very same time, both be quietly curious about each other, both even be actively listening, and still simply miss each other's comparatively short, loud broadcasting windows by centuries, passing each other in the dark without ever quite realizing it. There is one further idea worth naming honestly here, if only for a single careful sentence, because it deserves plain acknowledgement without deserving any lingering attention or added atmosphere. Some researchers and writers have proposed over the years that civilizations might choose to stay deliberately silent out of caution, keeping quiet on purpose, rather than by simple circumstance or coincidence. There is no real evidence supporting this particular idea, and it explains nothing at all that the quieter, more ordinary possibilities already explain just as well and just as gently. So we will set it down here exactly as carefully as we picked it up a moment ago and continue on with the rest of our own honest accounting. Taken all together, these quieter explanations return us, once again, to the same honest answer this whole night has been gradually circling around. The silence we have been sitting with may not, in the end, be any kind of verdict on how much company the wider universe actually holds. It may simply be, instead, a faithful reflection of how narrow, how young, and how particular our own listening has been so far, measured against the true and enormous scale of everything left still to check. There is one more quiet possibility worth including here, gentler than the rest, because it does not require anyone, anywhere, to be doing anything wrong at all. It may simply be that communication across such enormous distances is by its very nature a slow and infrequent thing, not because anyone is hiding and not because anyone has chosen the wrong frequency or the wrong medium, but because the sheer practical cost of sending a strong, deliberate, long-duration signal across many light years for an audience that may not exist and may not be listening, even if it does, is simply high enough that most civilizations, most of the time, quite reasonably choose to spend their attention and their resources on other things instead. Under this reading, the galaxy might be gently, unhurriedly quiet, not because it lacks company, but because a deliberate, sustained broadcast is, for almost anyone weighing the costs honestly, a comparatively rare and considered choice, made only occasionally, rather than a constant, ongoing activity. It is worth remembering, too, that our own listening equipment continues to improve in ways that quietly narrow this whole set of explanations, one careful year at a time. Newer radio receivers can now search far wider swaths of the spectrum simultaneously than the single narrow channel Drake was limited to in 1960. Newer computing techniques can sift through years of recorded data in the time it once took to review a single afternoon's worth. Each of these quiet, incremental improvements closes off, gently, one more version of the wrong frequency or wrong medium explanation, narrowing the honest range of possibilities a little further with every passing decade, even as it leaves the deeper, gentler truth of the matter exactly where this whole evening has been patiently placing it, that the sky's silence is a measurement still very much in progress. So far tonight, we have mostly asked what we have heard, or more precisely, what we have not heard. It is only fair and quietly worthwhile to turn the question carefully around and ask instead what we ourselves have actually said outward into the dark, because the honest answer turns out to be humbling in its own gentle way. On the 16th of November, 1974, scientists working at the Arecibo Observatory in Puerto Rico used its enormous dish, at the time the largest single radio telescope on the entire planet, to send a deliberate message outward into space for the very first time in a formal, planned way. The transmission itself lasted only about 3 minutes and consisted of exactly 1,679 individual bits of information. A number chosen quite deliberately because it happens to be the product of two prime numbers, 57 and 23, meaning there is only one sensible, unambiguous way to arrange those bits into a rectangular grid, 23 columns by 57 rows. Arranged correctly that way, the resulting grid forms a simple picture, built entirely from filled dots and blank spaces, depicting the numbers we ordinarily count with, a simplified sketch of the basic chemistry that makes life as we know it possible, a simplified outline of a human figure alongside a rough indication of human population, a small diagram of our own solar system, and a small drawing of the Arecibo dish itself that had sent the message in the first place. It was aimed carefully at a distant, dense cluster of stars called M13, sitting roughly 25,000 light-years away, understood from the very start by everyone involved to be far more of a public demonstration of the instrument's own remarkable power and precision than any genuine, realistic attempt at starting a conversation. By the time that message could possibly arrive at its intended destination, the star cluster it was originally aimed at will itself have shifted considerably in the sky, carried steadily along by its own slow, patient orbit around the wider galaxy. It is worth pausing for a moment on how carefully the Arecibo message itself was constructed, because the care put into it says something true about how this whole field approaches the act of speaking outward. Every choice embedded in that simple grid of dots, the numbers 1 through 10, written in a system any technological civilization might independently discover. The atomic numbers of the handful of elements essential to life as we know it. The double helix shape of our own genetic code was chosen specifically because it relied on mathematics and chemistry rather than on any particular human language, on the theory that arithmetic itself might be the one truly universal language available to two civilizations that had never previously spoken. Whether or not that theory ever gets tested by an actual reply, it reflects the same patient, careful thinking that shaped Drake's choice of the hydrogen line back in 1960, a repeated instinct across this whole history to reach first for whatever the universe itself already holds in common, rather than for anything uniquely and only our own. A few years earlier, and again a few years later, two other quiet efforts had already gone even further out into the dark, carried physically outward rather than simply broadcast as radio waves. Small metal plaques, carefully attached to the Pioneer 10 and Pioneer 11 spacecraft launched in 1972 and 1973 respectively, carried simple, carefully engraved images meant to explain, to whoever might conceivably find them someday in the far future, roughly where they had originally come from and who exactly had sent them. And in 1977, the two Voyager spacecraft each carried something considerably richer still, a golden phonograph record, carefully assembled by a small dedicated team that included Carl Sagan, Frank Drake, and the writer Anne Druyan, holding within it warm greetings recorded in dozens of different human languages, the recorded songs of humpback whales, and photographs depicting ordinary daily life here on Earth, mountains and rivers, and children and simple meals shared together around a table. Voyager 1, the more distant of the two spacecraft, continues drifting steadily outward. Even now, decades after its launch, its own radio signal growing fainter and fainter with each passing year, until eventually, at some point still ahead of us, it will fade below the point where even our most sensitive instruments can still reliably detect it at all. And yet the golden record itself will keep traveling long after that faint signal has gone quiet for good, carried onward by simple, patient momentum through the vast emptiness that lies between the stars. In roughly 40,000 years from now, according to careful calculations made by the mission's own scientists, it will pass within about 1.5 light years of a small, dim, quiet star called Gliese 445, coming considerably closer to that distant star than it will ever again come to our own familiar Sunday. Set beside 66 years of careful, patient listening, our own total deliberate output, honestly measured and added together, amounts to just a small handful of hours in total, spread thinly across half a century of human history. We have not, in any truly meaningful sense, been calling out loudly and receiving no answer in return. We have, instead, been listening far more and far more patiently than we have ever actually spoken outward ourselves. And the golden record now drifting quietly and steadily toward Gliese 445 may well be the closest thing to a genuine, heartfelt greeting our entire civilization has ever actually managed to send. It is worth adding one further, quieter message to this same short list, easy to overlook precisely because no one ever deliberately sent it at all. Every television broadcast, every radio program, every radar pulse Earth has ever produced continues traveling outward regardless, an unintentional signature of our civilization, spreading slowly through the surrounding dark, growing fainter year by year, exactly as we discussed earlier tonight. Somewhere out past the edge of our own solar system, a thin, expanding shell of our earliest broadcasts, faint and largely undetectable now even to us, continues moving steadily outward at the speed of light, carrying in its own accidental way the ordinary sound of an ordinary civilization, simply going about its business decades before anyone thought carefully about who might be listening on the other end. Taken together, our brief history of deliberate messages and our much longer, much quieter history of accidental ones tell a consistent, gentle story. We are, as a civilization, still extremely new to the idea of speaking outward on purpose, newer even than we are to listening for someone else doing the same. The 3 minutes at Arecibo, the 2 small plaques, and the 1 golden record represent, honestly, the entire deliberate output of a species that has existed for hundreds of thousands of years. Measured against that backdrop, it would be unreasonable to expect a reply already. We have barely cleared our own throat. Bring all of this, gently, carefully, into the present moment, right up to tonight. NASA operated its own formal, government-funded search for radio signals from other civilizations, beginning in 1992, only to see that same funding fully withdrawn by Congress a single year later, in 1993, on the stated grounds that the entire effort was considered too speculative to justify continued public spending during a tight budget year. The underlying work did not stop there. However, it simply moved quietly into the private sector, continuing on as Project Phoenix, which spent the following decade carefully, patiently examining several hundred of the nearest and most promising Sunday-like stars, using some of the largest and most capable radio telescopes available anywhere in the world at the time. Perhaps the warmest single chapter in this whole recent history began in 1999 with a modest project called SETI at home. Rather than relying entirely on a small, overworked number of professional scientists to manually sift through the truly enormous volumes of raw data these ongoing searches naturally produce, the project instead distributed tiny individual fragments of raw telescope data out across the early internet to be quietly analyzed using the idle, otherwise unused processing time, sitting on millions of ordinary home computers scattered all around the world. For more than 20 years, right up until the project finally, gracefully wound down in 2020, an enormous number of ordinary people, the overwhelming majority of whom will never appear in any astronomy textbook or receive any public credit at all, quietly let their own home computers join this vast, distributed search overnight, patiently sifting through fragments of the sky's own static, while they themselves lay sleeping peacefully nearby. It may well be the single gentlest image this entire search has ever produced across its whole history. An ordinary household computer, humming quietly to itself in a darkened room, doing its own small patient part to help listen to the stars, while its owner rests undisturbed only a few feet away. Today, the search continues on a considerably larger scale than at any point in its history. The Allen Telescope Array, situated in a remote part of Northern California, and built specifically with this kind of large-scale survey work in mind, continues its own patient, ongoing work night after night. In Guizhou province in southwestern China, an enormous radio dish, 500 meters across, and currently the largest single-filled dish anywhere on the planet, adds its own considerable listening power to the wider international effort. The Breakthrough Listen program continues steadily publishing its careful surveys of the nearest million stars, openly and freely, for any researcher anywhere in the world to examine and build upon in turn. And newer optical search programs now scan patiently across the sky for brief pulses of light lasting less than a single billionth of a second. An entirely new technology that simply did not exist yet when Drake first sat quietly in that small equipment room back in 1960, headphones pressed to his ears. What is perhaps most remarkable of all about this whole modern chapter of the search is simply how quiet and how thoroughly automated it has gradually become over time. The instruments themselves run largely on their own, now patiently gathering data steadily through each night, needing no single dedicated person to stay awake and hold the headphones in place the way Drake once quietly did, alone, on that first cold morning. Somewhere, at almost any given hour of any given night, some fraction of this vast, ongoing listening effort is quietly underway, entirely whether or not anyone in particular happens to be watching closely at that exact moment. The search that began all those years ago with just one man alone in one small room on one quiet hillside has slowly, gently become something closer to a slow, patient, planet-wide habit now, carried on gently and steadily in the background of ordinary daily life, largely unnoticed by the millions of people it quietly, faithfully serves. There is a quiet symmetry worth noticing between this modern chapter and the very first one we told tonight. Drake once sat alone with a single set of headphones, listening by ear for anything that might stand out from the ordinary hiss. Today's instruments generate such enormous volumes of recorded data, gathered continuously across huge swaths of the radio spectrum, that no human ear or human eye could ever hope to review even a small fraction of it directly. Instead, specially designed software patiently combs through the recordings automatically, flagging anything unusual for a human researcher to examine only afterward, exactly the way Eamon once sat down with a printed page from Big Ear and circled one unusual sequence by hand. The tools have grown almost unrecognizably more capable across 66 years, and yet the underlying rhythm of patient automated listening, followed by careful human verification, has hardly changed at all. Consider, too, how the Breakthrough Listen program in particular has made a deliberate point of publishing its full data archive openly, freely accessible to any researcher, student, or curious member of the public anywhere in the world who wishes to look through it directly, rather than keeping the raw recordings locked away within a single institution. That choice, small as it might sound, matters a great deal to how this whole search understands itself. It is not a private hunt carried out by a handful of specialists working in isolation. It is closer to a shared generational project, openly inviting anyone patient enough to look carefully at the data, to become part of the same long, quiet effort Drake began with 2 ordinary stars and 200 hours of careful listening. Even the newest optical searches, watching for those impossibly brief pulses of light, lasting less than a billionth of a second, follow the exact same quiet discipline established all the way back at Green Bank. Candidate signals are checked and rechecked and shared openly among independent teams before anyone allows themselves to feel any real excitement about them. 66 years on, the method has scarcely changed at all, even as the instruments themselves have grown almost unrecognizably more capable. Patience, verification, and an open shared record remain, exactly as they were on that first spring morning, the whole quiet architecture of the search. Let us go back now, one final time tonight, to that same quiet hillside in West Virginia, to the spring morning in 1960, when all of this long, patient story first began. Picture, once more, the same young man, the same worn set of headphones, the same steady, patient hiss arriving faithfully from an ordinary star some 11 light years away. Hear it again gently, now with everything we have carefully gathered together across this whole long night resting quietly alongside it. Notice gently how far that hillside has carried us tonight, and how little, in the end, actually needed to change about the picture itself to make the whole story feel different. The dish is the same dish, the stars are the same stars. Only the listener's own understanding has grown larger around them. The way a familiar room looks different once a lamp is finally turned on in one of its corners. That static was never, in any real sense, the sound of an empty room. It was, and in its own quiet way still is, the sound of an unfinished universe arriving faithfully to us every single second of every night from countless stars that have not yet finished the long patient sentence they are still, even now, quietly in the middle of speaking. We have listened carefully and honestly to a single page drawn from an almost endless library and found, so far, no message written plainly upon it. But we now understand, gently and without any need whatsoever for alarm, that the reasonable, measured response to one quiet page is never to conclude, hastily, that every remaining shelf in that vast library must therefore be entirely empty too. It is simply, and only, to understand more clearly just how very much of that library still remains unread, waiting patiently for whoever comes next. There is nothing left to add to the arithmetic tonight. We have walked the whole shape of it together, from one dish and two ordinary stars, out through a blackboard equation, a lunch table question, a catalogue of thousands of worlds, 4 honest almosts, an unmeasured library, a long wait written into the age of the galaxy itself, our own quiet reflection in that same wait, and a handful of gentle reasons. The sky may simply not have finished speaking yet. Each piece, taken alone, might have sounded like an answer. Taken together, gently, they sound instead like exactly what they are. A patient species, still quite young, still listening carefully, still willing to wait, widen the view, one final time tonight, out past that first small dish and its first small hillside. Somewhere out there tonight, other dishes are turning too, patient and unhurried. Larger ones now, quieter ones. Some of them run almost entirely by machines that need no single person awake at all to tend them through the night. They tilt slowly upward hour after hour, exactly as that very first dish once did, patient in a way that asks absolutely nothing of anyone watching. The listening never really stopped, not even for a single year. It simply grew large enough, and steady enough, and quiet enough that it no longer requires any one particular person to stay up through the long night, holding it carefully in place with nothing but their own patient attention. So let the static settle gently around you now, the same way it once settled around one young astronomer 66 years ago in a small room on a cold hillside before dawn. You do not need to bring back an answer with you tonight. Nothing in this whole long story has ever truly asked that of you. The dishes will keep turning long after you yourself have drifted off into sleep, patient and unhurried, quietly listening on your behalf, while you rest completely undisturbed. Somewhere between the first quiet page of that endless library and whatever page finally holds an answer, if one is ever found at all, there is simply this long, patient, ordinary work of listening, carried gently forward by one generation and handed just as gently to the next. You were not asked to finish it tonight. You were only asked to rest inside it for a while, the way countless quiet nights have rested inside it before you, and countless more will rest inside it after. The stars themselves are in no hurry. Neither tonight do you need to be. Rest now. Good night.